Hello everyone. I've been reading a bit lately about sampling oscilloscopes and all related to this type of technology. And today I'd like to record a bit of the things I found. Could be useful, at least for me, to help me organizing my ideas and deciding next steps with this very interesting technology. Um, I suggest everybody start with this video from Yapo. Um, I was Years ago I was exposed to the concept of subsampling in digital signals. But in this video helped me to discover that some instrumentation companies, they manufacture instruments that in order to explore very quick signals, they build those devices and they sold them. And there is a whole universe of this technology out there, and some of those devices might be 20 or even 30 years old, so you can find them in the wild. So yes, this is this presentation. This is an amazing presentation where Ted goes through his journey in this technology, in sampling oscilloscopes, um, explains the basics, a lot of information. I've watched this presentation a number of times because it's very rich. Sometimes in concepts that Ted just mentioned in passing could give you a couple of hours of research online. Um, and he goes into details of his project to to build his own sampling oscilloscope. He managed to do it. He also explains all the methods he used to characterize it, to see how good it is, how bad it is, and practical applications, doing time domain reflectometry, analyzing the characteristics of circuits. Again, it's I cannot emphasize it. It's a great presentation. Unfortunately, but I don't think the project made it to the public. There's some information in Hackaday. You can find some schematics. There is a forum, but I don't see anywhere to acquire or to to use his invention. So if I'm wrong, please, yeah, here we have it. This is his project. So if there is any way to find it, build by somebody that knows what he's doing. So that'd be that'd be great. That'd be great to know. There are other videos online that explain you the concept of sampling oscilloscope. It took me. It's one of those things that the explanation is quick and easy, but it takes some time to register. It took me some time, at least, for me to register in my head. So all those links will be in the description. I suggest you to start with the Yapo presentation. And then there are a couple of videos from the signal path, very well done. And in the signal path 83, there is a description of how digital sampling oscilloscopes work. In this case, it's an Agilent. This part, this introduces a bit of the complexity in this technology. Different manufacturers, they name their products differently. There is a bit of overlapping with some technologies, and this could be a bit confusing. That's why I decided to share some different videos so we can get a global view of how the industry approached these technologies some time ago. In this case, this video in the signal path, I like this diagram, because in this technology you have a very fast signal flowing, and you take consecutive samples that you will be delaying over time. So in this graph it shows you how you take a sample in a point of time, you let the signal pass, and then you take another sample almost in the same time. So you need to be sampling oscilloscopes, they need to be very accurate when it comes to repeating the sample at the same time, and they have to be very accurate to delay the sampling in a small amount every time. So this is the way they have to reconstruct the signal eventually. The signal path has another video where they go deeper into this technology again. Great presentation, great comments as always. I suggest you to go also through it. Very good explanations between the difference between a real-time oscilloscope and a sampling oscilloscope. And we can see here another case of an Agilent sampling oscilloscope with modular technology, and this will be a common theme in this video, where we will see that what I think is kind of uncommon in the world of oscilloscopes. We can see how different manufacturers decided to put the sampling logic in external modules that can be designed with different frequency ranges and different characteristics. I'm going to link also this video from the Curious Marc. That is a video that I like a lot, where this technology is also explained again from a very good YouTuber, but from the analog point of view. So there are many instruments that they approach this technology with digital sampling, but the fundamentals can be approached as well with analog technology. In this case, from the this technology is from the this counter is from the late 60s, but this module, this prescaler is from the 70s, if I remember correctly. So very good presentation, where like Ted Yapo does in his presentation. We can see details. We can see a low-level explanation of this technology, and here we have it again with Curious Marc, where he goes deeply in a masterful way into the schematics of this prescaler, and yeah, really spending some time watching this video, you get again a good view of the fundamental, where we're again in the same. I don't want to try to explain what they're explain it, because I won't do a better job. But again, you have a strop signal. We're starting to see here how diodes are being used, how the role they'll play, why. Here is a good presentation, it's a good explanation as well, that why we have two of them to prevent the strop signal to go into the input. But the concept is the same. we have a very fast signal at the beginning. In this case, this was designed to to provide this. This was designed to provide this frequency meter with a way to be able to count frequencies much higher. This frequency meter is the limit is 50 megahertz. In I think this prescaler allows you to go if I remember correctly 14 gigahertz or 18 gigahertz. We cannot say it, but you get the idea. In the case of this prescaler, that strobe, that signal that allows you to sample the signal is created locally, and in this case, Marc is tapping into the result of that mixing. So the strobe is triggering the diode, is sampling the frequency, and he can see the output on a normal oscilloscope. Also very interesting. I'll be talking about devices from Tektronix because I guess the only special reason is that the video that got me going from about this was this one, and Tektronix was mentioned. So there are other manufacturers, there are other solutions. Perhaps we can explore them in the future, but today I'll be talking about Tektronix because that's the one that started with when it comes to learning about this. This according to Wikipedia, this is the oscilloscopes series that popularized this technology in Tektronix, the 7000. As you can see, a very modular technology. In some of those modules allow you to sample, again, with the same idea to bring into the oscilloscope a signal that is much higher than what the oscilloscope can handle. And there is an impressive collection of sampling heads. Here we got introduced for first time to the concept of sampling heads. According to this, an impressive frequencies, 11 gigahertz in 1972, 14 gigahertz 1968. But the concept is the same. We will get either from the device or from an external source a strobe signal. This will use a sampling diode to get samples of this signal, and this will help us to reveal the signal inside the device. And then later, a device that I find fascinating, the 11801 from the 11800 series. We see in this case not an oscilloscope or not a frequency meter that is adapted for this purpose. This is a device fully, a fully designed oscilloscope to do this task. Pure sample oscilloscope, where with slots for 4 heads. And very peculiar device from the 90s with touchscreen and vertical a vertical monitor that I find very interesting. And it came with its own collection of sampling heads. And also they introduce optical sample heads with you can plug a fiber optic with a digital signal, or an analog signal or a digital signal modulated, and you could convert it from the from optical to electrical and bring it back into the instrument. Impressive 50 gigahertz sampling head with some optical to electrical converters. There is in this series basically there are a number of versions, and they are very similar among them. I guess there are evolutions, but if you look for information about the 11800 series, you'll find that the 803 is part of this family. It is peculiar because the name changes. I guess people in marketing began to explore different acronyms, different architectures, and here we can see how different name is introduced: communication signal analyzer, which I guess helps when it comes to explaining what those devices do. In this case, we don't have 4 fully functional slots for sampling heads. Those 2 slots on the left they only provide power, so they were used to insert heads that were intermediate stage, like those optical to electrical heads we have seen. So one slot is used to power that head, and the other 2 slots are used to place the heads that are going to do the sampling. Which I wanted to mention because it's weird when I was doing the research, the 803 was popping up, but yeah, as you can see, they belong to the same family. Interesting information online regarding how over the years Tektronix have been changing the technology of the sampling head with different configurations. And here we begin to see what they call the traveling wave sampler, and we can see that we have 6 diodes. In some documentation they refer to 4 diodes. And I find this interesting because when we see pictures online, when people open those sampling heads, we put some time, we can begin to recognize those structures. This is a very nice picture from Leo Bodnar of the SD26 sampling head. This is a dual input sampling head, which is future. There are other versions that they incorporate TDR, time domain reflectometry in circuits in this area. There are other versions. We can see that this head was prepared for that but didn't equip TDR, and with dual heads and TDR we can measure impedance of circuits, of transmission lines, differential transmission lines, and this is why those dual heads are very sought after. So if we zoom in, we can see the input, and as a dual head there are 2 very similar structures. So basically one is the mirror of the other. So I guess this is the it's not letting me, yeah. So we can see that this part is basically the mirror of the one below. This is the input, and we can see what it seems to be the either 4 diodes, depend how we count them, or if those guys over here, they are diodes as well. They could be 6 diodes. I don't know that, but it resembles this structure from the wiki. So I've been, yeah, I've been reading a bit about it, getting a better idea of how those things work, and maybe we can explore that again in the future. Then there is this small departure, the TDS 820 and the 840. I guess here Tektronix was exploring a way to keep building those oscilloscopes, but without, I guess, the additional cost of the sampling heads and what it comes with them. And they decided to create this sampling oscilloscope that has no heads. Well, that's not true. It has them internally. Let's call it. Let's say that it doesn't have modular heads. But I find that weird because, as you can see, it's at 8 gigahertz sampling oscilloscope that is no modular. You can either buy it the 820 with two inputs and the 840 with 4 inputs. And compared to, yeah, what we were seeing earlier, compared to those frequency ranges that its cousin has, it's hard to guess what gap this oscilloscope was trying to fill. But we're exploring the Tektronix lineup, and this is part of it. In more conventional format oscilloscope. And in the wiki, they mention the head technology that is built inside. We can see it from an eBay picture. This is the acquisition board of an 820. We know that it's an 820 among other reasons because we can see that it has 2 heads inside, and it has the space to be populated for the version 840 with two more. So yeah, internal heads for some reason. Very nice pictures again in the wiki. Input, the 4 diode structure, and what could be also 2 diodes here, aligning a bit with that diagram we have seen earlier. Interesting case, but yeah, when you see the characteristics of the 11800 series, it makes you think that what application is what those smaller versions were targeting. Anyway, and then in late 90s, the 8000 and CSA 800 CSA 800 and TDS 8000 were introduced, and this seems to be a bit of the culmination of Tektronix during a number of years of building those instruments. Very impressive devices. We have more slots. We have 4 slots with this very similar to what we have seen in the 11800 series, and 2 more slots for bigger applications up here, and yeah, up to 70 gigahertz. Very, very impressive. There are a number of versions, as you can see here, the 8000, the 8200, in different flavors, in the flavor of the computer signal analyzer, and which I guess is different hardware characteristics and different software, mainly for different applications. You can see them a lot around. I think Tektronix stopped selling them and making them in 2023. So 20 years of history, they are around, even in very recent. You can see people using them in professional labs in a number of in a number of places. But of course, when you go to the official website, you get the notice that they are not selling them anymore. Uh, we This is where we start beginning to see instruments that have a Microsoft Windows interface, and this in when I came across this for the first time, it was a bit of disappointment. After seeing many instruments with those fantastic, you know, as, more classic, more classic screens. I was a bit disappointed to see that. Well, yes, this is just a Windows, not a lot of resolution and all those things. But then I learned that in this type of instrument, Microsoft Windows play the role of a UI basically. Uh, this is the back of the instrument, and at the top it has a PC basically, an Intel PC with standard PC components and a standard PC I/O. So that's the part that the computer uses to talk with us and the network and other devices with a CD-ROM and standard hard disk. But the magic really happens in this board below. And this is a very interesting board. Yeah. So the core of the oscilloscope is this computer basically. This is a full computer in a board powered with PowerPC. Through this slot, it communicates with Intel PC that is on top of it, running Microsoft Windows. And through this bus talks to the acquisition board. Those devices, they have an impressive acquisition board with a lot of FPGAs that they do. That's the part that is talking with those slots where the sampling heads reside. In this computer uses a real-time operating system that I didn't know that existed, to be honest. A full real-time operating system, which is its own its own thing, running specialized software that Tektronix has created to talk with the acquisition board. According to a couple of videos I've seen, this is a proprietary serial bus, but some people have managed to plug into this connector and interface with the operating system and fix it and changing parameters. So I find it very very interesting. The slots that have the sampling heads below, they are very similar to the sampling heads we can find in the 11800 series. I'd say that the size of them is exactly the same size. Not the size, the size of the slot. So how I'd say that this part is identical to the 11800, but those slots, those heads are longer. We can see here in this video. We'll see later when it's fully open. Yeah. So I'd say that those heads are longer. They include functions that they are not present in the 11800. For instance, they have power meters, so you can plug an external component to measure the power of the signal you are acquiring. We go to the previous picture. We can see that the heads in the 11800 are shorter and don't have any way to measure power. But in this case of these guys, they have it's a dual. They have the room to add the same functions we have in the 11800, but as well adding power meters over here. And when the head is open, we can see a very similar structure. In this case, this head has TDR, and this is the part where the circuit of the TDR is located. It was empty in this part. This part was empty before. And very similar, just longer. So that makes me think that the sampling head technology between the 11800 series heads and the 8000 is going to be very similar. Plenty of information, but yeah, it's the evolution of this technology from Tektronix in the early 2000s, and has been solved until recently. And here we have a good example of how to use this technology practically. In many cases is people use it to analyze the impedance of circuits. In this case, of a connector. So you can use you can see what's the impedance response through different configurations, where the circuit is open or the circuit is short, and how different components. This is a very simple case where you have just a connector, but in many cases you can have connector, cables, and you want to see at high frequencies the response of those components. An interesting thing to notice that you may not see at the beginning is that the unit at the bottom is a distance, physical distance. So we're very used to see those graphs and we don't pay attention, but in the case of TDR, and it's this axis is distance, which I find that very interesting. We can see in action one of those devices. Here is somebody trying to analyze the behavior of a cable. Again, this is TDR. In the bottom axis we have distance, and we can see how the graph changes. The impedance changes when we are adding more cables, adding connectors, and in this with those instruments you can see it in real time for very high frequencies. A very interesting video of Bill Hurt. Bill Hurt has also this type of instruments, and in another example he's working with this gentleman over here, learning how circuit layouts and type of substrate changes the behavior of impedance. And in this case it's a differential communications line, and we can see how again in real time how this changing the shape of the cables, everything impacts impedance, and you can see it in real time, which I find it very interesting. I will link all those videos, and so you can enjoy them as well. And I don't think there is anything else between the 8000 and now. If we go to the Tektronix webpage, we can see those very interesting devices. Tektronix called them oscilloscopes. We don't see the word sampling oscilloscope anymore. And those are oscilloscopes with very impressive features. So basically those are real-time oscilloscopes that are going to be sampling at 200 gigabytes per second. And this links with something that Ted Yapo mentioned in his presentation, that the industry is moving to real time. The industry is moving to sampling everything, put that through FPGAs and memory and CPUs, and once you have it inside the computer, you can do whatever you want. The challenge here is that those devices are very expensive. I have no idea how much this cost, but I wouldn't be surprised that a real-time sampling oscilloscope and of 200 giga samples per second could cost you $120,000 or $150,000. And yes, and Ted mentioned this, that in the future we won't be able to wait 10 or 20 years to buy one of those devices that is cheap. It's going to be very hard to find those devices as cheap in the market in a number of years, and those all guys are going away. So for hobbyists, we are losing the potential of buying all devices to do digital sampling in those type of measurements in the future. Those devices are still there. I'm keeping an eye on the market. Unfortunately, you can find some of them that are broken, cheap and broken, and yeah, there there are videos online of people fixing those, and they are very inspiring, but they look at me they make it look easy, and it's not easy at all. You need a lab. You need a laboratory at home to fix instrumentation, so it's a hard thing to do. And but yes, this is my quick sharing of what I've learned of sampling oscilloscopes, in this case from Tektronix. And if I misunderstood anything, just let me know in the comments. I'm happy to learn.